Now, mobility and degrees of freedom are similar properties, but they don't always match. So mobility is something that's found by an equation. That is Gruebler's equation. M equals 3 times number of links minus 1 minus 2 times total joint order. Now, degrees of freedom is number of independent coordinates required to completely specify position, or another way to think about it is number of actuators required. Or number of independent ways the system could move. Now, usually mobility and degrees of freedom are the same, unless there's something weird about the mechanism, like some kind of strange shape that makes it move in ways that it otherwise wouldn't be able to. So we will look at two examples here of adjustable weight benches, one of which will have mobilities and degree of freedom match, and one of which won't. So we need to start out by drawing the kinematic diagrams for each of these. And we're going to look just at the back part and not the seat part of the bench because these are symmetrical. So focus just on the back part for these. So drawing the kinematic diagram, so we have the ground here, and ground is always all one link. So even though there's that sort of stem in the middle, and then there's the flat base, the stem and the base don't move relative to each other. So that's just one link. So then we'll have a revolute joint. We'll have another revolute joint up here. And then where these connect, there is a prismatic joint. So then the seat back is connected with a revolute joint there, and the seat back is all one rigid thing. So let's count up. For links, we have one link. So ground is all one. We have 2, that's the seat back. And then this extending rod is going to be 3, 4, because there's a socket of the rod and there's the actual part that extends out, similarly to the way a pneumatic or hydraulic cylinder would work. So 4 links, and now we'll count up joints. So we have one joint here, that's revolute, another revolute 2, another revolute 3, and then a prismatic 4. So J equals 4, and that is 3 revolute, 1 prismatic. So the mobility for this one, we use the M equation. M equals 3 times L minus 1, which would be 4 minus 1 minus 2 times J, which is 4. So 9 minus 8 equals 1. So 1 equals mobility. And looking at this, degrees of freedom, well, that's how many independent things could we control. Basically, what you do is you pull out that yellow rod, and that allows the slider to adjust. So that's 1 degree of freedom. How far you adjust the slider, then the angle of the seat just kind of is whatever it has to be to match for the height of that slider. So degrees of freedom here equals 1. And then we see that degrees of freedom is 1, M equals 1, they match. So degrees of freedom equals M equals 1 for this weight bench. Now looking at the other weight bench, we see this should also have 1 degree of freedom because you pull out the pin that's right here, and then you can adjust the angle of the back of the seat. So here, degrees of freedom equals 1. Let's draw the kinematic diagram from this. So we'll have the frame. See, it's kind of hard to see. So we've got this frame. So this is ground. And then we've got the seat, which this curved link is all connected to the back of the seat. So we have 1, 2 links. L equals 2. One is the seat with the curved rod, and one is the frame. And then joints, let's see, we have the prismatic joint right here. It's that slot that the curved part of the bar is going to, so that's 1. And then we have the pivot for the seat, which is 2. So J equals 2. So now looking at this one, if we do the M equation, M equals 3 times 2 minus 1 minus 2 times J, which is 2. So equals 3 minus 4 equals -1. So here, mobility and degrees of freedom do not match. And that's because of that curved bar. If that bar were straight, then you would need an extra joint. You would need it to be able to slide or something like it. You wouldn't be able to do this with just 2 degrees of freedom, with just 2 links and 2 joints. You would have to use 4 links and 4 joints like the red bench.